Chapter 14 is all about acids and bases and how they have two different phases. I posted in the first level 62 video that song, so check it out. It's pretty funny. The nature of acids and bases, we can classify them on how they taste and how they feel. So acids taste very sour. Vinegar is actually acetic acid, and lemons contain citric acid. Bases, which we can also call alkalis, like we have alkaline earth metals and alkali metals, alkalis, taste pretty bitter, and they actually have a slippery feel to them. Most cleaning solutions or soap are highly basic. They are bases. Sponte Arrhenius was the first person to actually recognize the nature of acids and bases, and he was able to postulate from his experiments that acids produce hydrogen ions in aqueous solution and bases produce hydroxide ions in aqueous solution. His concept was a major step forward so that we could quantify acid-base chemistry. His concept was very limited though, because first of all, it only applied to aqueous solutions, which that's not true, we know now, and it only allows for one kind of base, which is the hydroxide ion. But not every base has hydroxide. So a more general definition of acids and bases was suggested by Johannes Bronsted and Thomas Lowry, where they said that an acid is anything that donates a proton, which the proton would be an H+1, the hydrogen ion, and a base would be the proton acceptor. So acid is what's getting rid of the proton, and base is what is gaining the proton. So for example, when you have hydrochloric acid dissolved in water, the hydrochloric acid molecule donates a proton to a water molecule and so qualifies as a Bronsted-Lowry acid, which you can see here, but you don't need to write it down unless you really want to. So the hydrochloric acid gives this proton right here to the water to make this H3O plus 1 molecule, which we call that H3O plus 1 hydronium ion. So hydronium we're actually going to see a lot. This is a space filling model, another way to recognize that the reaction happened. For any general reaction of an acid dissolved in water, you take your acid and your base, which is usually water, and you are able to come up with what's called the conjugate acid and the conjugate base. First off, this arrow is really supposed to be our equilibrium arrow back from chapter 13, but I just can't find a way to put it on there yet. And so the A stands for anion. H in front tells it's an acid, because every acid starts with H, and because that's the proton. And then the A stands for anion. So this could really apply to any acid, okay? So the conjugate base is everything that remains in the acid after one proton is lost. So when you lose that H plus 1, then you have what's left over in the conjugate base. The conjugate acid is formed when the proton is transferred to the base. So it's the base plus the H plus 1 to make the conjugate acid. When we have these acid bases and conjugate acid and conjugate base, then we can make what's called a conjugate acid-base pair, where you can pair up what's related to each other in the reaction. So looking at the same reaction as before, the pairs are the acid with the conjugate base and the base with the conjugate acid. So in this case, we have HA and A minus 1 paired up, and then we have H2O and the hydronium paired up. Okay, it's almost like when you are doing double replacement where it's outsides and insides. Okay, but this pairing helps us with our understanding acids and bases and all of that. So when you have this transfer of the proton, there's actually competition between the two bases, both the regular base and the conjugate base. If water is a much stronger base than the conjugate base, the A minus 1, which means that water has a greater affinity, meaning that the water wants the proton more so that it can form the hydronium ion, then the equilibrium will be far to the right. So in case you forget what that means, far to the right means that you're going to have more products present than reactants. So products will be greater than the reactant species in the equilibrium sample. And by doing this, with being more with the product side, then that means that we're going to have the hydronium, and we're going to have the conjugate base. If instead the conjugate base is a much stronger base than the water, then the equilibrium position will lie far to the left, meaning that instead the reactants will be greater than the products. In this case, most of the acid dissolved will be present at equilibrium as its original acid. It won't be broken up. We can still write equilibrium expressions for our acids dissolving. Ka is called the acid dissociation constant. We still set it up the same way, products over reactants, but notice how water is not included because we can assume that the concentration of liquid water remains essentially constant, meaning that it's not going to change. So just like in chapter 13, if we have a liquid or a solid, we're not going to include it. Same here. Okay. Notice how you actually can, instead of writing the hydronium H3O plus 1, you can just write H plus 1 instead if you want to be lazy. But when we take that out, then instead we can come up with our new equilibrium expression from the new reaction. When you take out the H2O, you also take out the hydronium because you can't have oxygens on both sides if they're not there. And so then the equilibrium expression will be the same as what was on the right, up above. Note that we use Ka to represent only the equation that's here above, not the one with water in it. But by knowing this, you can write the Ka expression for any acid, even one that's totally unfamiliar. And that's, again, because the A minus 1 means anion. So we could write this expression for hydrochloric acid, where it's HCl. We could write it for sulfuric acid, H2SO4, where the anion is what changes, but the H does not, because that's a characteristic of being an acid, having an H in front. Okay? Even though it's not included, don't forget that water plays an important role. We just don't include it to simplify our lives. So for example 1, let's write the dissociation reactions, not including water, for each of the following acids. So for A, for hydrochloric acid, I'm only going to write states of matter on the first one. To save time, I'm not going to write them on the next couple. So we'll have our hydrochloric acid and then our equilibrium arrow, and we take out one proton, so we take out one H plus 1, and then what's left over is written as the conjugate base. So we have chlorine, and if it started out neutral charge, and we take out a positive, that means we're left with a negative to make it equal back to neutral. And that's it for A. For B, we have acetic acid, which is HC2H3O2. Oftentimes, or sometimes, acetic acid is actually written differently. But I write it this way just because it's easier to tell the proton that you lose. So when you take off the proton, then what's left over? Well, we're going to take off this first proton. So what's left over is our acetate ion with a -1 charge. Again, if you want to put states of matter, you go for it. Okay. C, we have the ammonium ion, which is NH4 plus. And so we're going to take out our proton. And so how we figure this one out is we subtract from the total number of H's. So now we have NH3 because we took out one H. And it started with a positive charge, but if we take that positive charge away, now it's just neutral. So that's it, NH3, which is actually ammonia. And for D, the anilium ion, we have our huge thing here. And that breaks down into, we're going to take off our H plus 1. And then what is left, let's take it off of the end H's this time. So we'll have C6H5NH2. And no charge because it was positive. So writing out the dissociation reactions are actually pretty easy. I don't ask for it here, but you may have to figure out the K expression. So then the Ka would be, like let's do for the first one, for A, the hydrochloric acid, the Ka would simply be products over reactants. So you would have the concentration of the hydrogen times the concentration of the chlorine over the concentration of the HCl. Just like that. So not really anything too different from what we did previously. But it doesn't stay that easy. So, just so you know, we could actually use these for gases as well. Just like how we did in Chapter 13, we were able to use molarity, or we were able to use gas units. For example, when you combine ammonia with hydrochloric acid gases, both, then it creates ammonium chloride, which I know it might be difficult to see, but there's this space right here in the middle when the two gases meet, and that forms a solid. So when you do have this, if you form an ionic compound, it may be a solid. It depends on its solubility. If it was an aqueous solution, it's probably going to remain aqueous. So, just so you know. Well, with our acids, we can actually figure out acid strength. It's defined by the equilibrium position for the reaction. So a strong acid is one where the equilibrium lies far to the right, meaning that almost all of the original acid, the HA, is dissociated or broken up. So that means we're going to favor the product side. We're going to favor these products. There's going to be more products present than there are reactants. A strong acid yields a weak conjugate base, one that has a low affinity for the proton. So that means that it won't want the proton, it wants to get rid of the proton, and so that's how it will work. So another way to phrase it is the conjugate base of a strong acid is a much weaker base than the water that's on the reactant side. A weak acid, on the other hand, is one where the equilibrium lies far to the left, meaning that most of the original acid is still present in its original form at equilibrium because it's on the reactant side. So it only breaks down a little bit. A weak acid has a conjugate base that is much stronger than the water, meaning that it wants to gain that, it wants to lose that hydrogen ion so that it can form the conjugate base. The weaker the acid, the stronger the conjugate base. This table, 14.1, is in your note packet, and I just included this. It's kind of a summary of all this information so far. Note that when you have a strong acid, the Ka is large, meaning that there's more products present. And when you have a weak acid, the Ka is small, so it's far to the left, meaning that reactants are favored. Okay? And so, good summary of information. This is a list of common strong and common weak acids. There's actually a total of 7 strong acids, but I only included some for your enjoyment, I guess. For the weak acids, there are many, many different weak acids. So these are just a sampling of what we could see. But the sulfuric acid, for example, is H2SO4. That H2 tells us that sulfuric acid is actually a diprotic acid, meaning that it has 2 acidic protons. So we could do the math for losing 1 proton, and then we could do the math again for losing 2 protons. Okay? So we're going to get into that in level 65. We also have acids that are called oxyacids, which means that the acidic proton is attached to an oxygen atom. Usually organic acids have this, where we have what's called a carboxyl group or a carboxylic acid, where the hydrogen is connected to the oxygen. Some of the most important acids that we use don't have the acidic proton attached to an oxygen. They're actually, a lot of them are attached to halogen atoms, so we call them hydrohalic acids, where the anion is from group 7A, the halogens. Okay, so table 14.2 I have right here is a summary of a lot of acids and their values for Ka, but notice how none of the strong acids are listed, and that's because they completely dissociate, so we can't really measure the value or the concentration of that original acid at equilibrium, because it's not really there. Also, I want to point out that the larger the Ka, that means that you have a weaker conjugate base, and that's going to be important for example 2. So using our table that we just saw, arrange the following species according to their strengths as bases. So we have water, and then we have a bunch of anions. So let's look up their Kas first to help us figure this out. So we're looking for acids in table 14.2 on page 4 of your notes. that contain the anion. Well, water isn't listed, so water doesn't have anything. Then we have fluoride, F, and that is contained in the hydrofluoric acid, HF. And HF has a Ka of 7.2 times 10 to the negative 4. Then next we have Cl. When that forms an acid, we'd have HCl, hydrofluoric acid, but that is a strong acid. So it's not listed on our table. Okay, then we have NO2, nitrite, and so we have nitrous acid when it's in there, and the Ka for that is 4.0 times 10 to the negative 4. And last but not least, we have Cn, cyanide, and that makes hydrocyanic acid, HCN, and that is a weak base, or weak acid, excuse me, so that would be Ka of 6.2 times 10 to the negative 10. Okay, so let's list these according to their strengths. Let's go weak to strong. Okay, well, first off, the strongest base will have the weakest acid. It's like opposite. Or the strongest acid is going to have the weakest base. So if we have a strong acid here listed, HCl, that means that that is the strongest acid, so the conjugate base of HCl, the Cl minus, is actually going to be the weakest base. So we can list that first. Okay. Then we have H2O, that doesn't have a number either, and then we have numbers. And the stronger, the larger the Ka, the weaker the base. So, just a hint, water is a stronger base than the conjugate base of a strong acid. So it's going to be stronger than our HCl, but weaker than the conjugate base of weak acids. So, if it's stronger than a strong acid, but weaker than weak acids, that means that water comes next, because all the rest of them are weak acids. Okay, so now we have our other three to deal with. Well, the weaker the acid, the stronger the conjugate base, or the larger the Ka, the weaker the conjugate base. So we have a really small Ka with Cn, HCN, 6.2 times 10 to the negative 10. So that is actually, times 10 to the negative 10 is actually smaller than times 10 to the negative 4. So that means that the Cn is actually going to be our strongest base. Alright, so then now we just have to figure out which comes next, the F or the NO2. Well, since they both have times 10 to the negative 4, now we have to look at what's in front of the times 10. Remember, negative on the times 10 means it's a decimal. 7.2 versus 4.0. Well, 7.2 is bigger. So the larger the Ka, the weaker the conjugate base. So that means that F will come next, third, and then the NO2 will come fourth. So it's a lot of backwards thinking about it, but you just gotta get your mind in the right mindset, and then you're able to do it. I know you can. Alright, a little bit more. So water can act actually as both an acid and a base, and we call those amphoretic substances, which water is the most common that we come into contact with. So when you have a water react with a water, you make hydronium and hydroxide. So when we're doing this, we kind of have to decide, well, which one's going to be acid, which one's going to be the water, because they both, one of them loses a proton and the other one gains a proton, so we're still having an acid-base relationship here. So amphoretic means that they act both as an acid and a base. With the ionization of water, we can figure out an equilibrium expression of the water, where it's, well, Kw, which we call the ion product constant, or the dissociation constant for water, is the product of the concentration of the hydrogen times the concentration of the hydroxide. So from experiment at 25 degrees Celsius, we see that the hydrogen is equal to the hydroxide when it's equal to 1 times 10 to the negative 7 molar. So meaning that at 25 degrees Celsius, Kw, when you multiply the 2, is equal to 1 times 10 to the negative 14. So that's super important. Make sure that you see that Kw is equal to 1 times 10 to the negative 14. Using our Kw, we can figure things out to know if they're neutral, acidic, or basic solutions that we're dealing with. So when it's a neutral solution, that means that the H plus is equal to the OH minus. When it's acidic, that means the H plus is greater than the OH minus. And the basic solution is when the hydroxide is bigger than the hydrogen. So for each case, Kw is equal to the H plus times the OH minus concentrations in molarity, and that equals 1 times 10 to the negative 14. So let's use this equation for example 3. Be sure to note that Kw is temperature dependent. So if it's not at 25 degrees Celsius, then you can't use 1 times 10 to the negative 14. So let's calculate. We need both the H plus and the OH minus, so calculate the one you don't have, and then tell me if it's neutral, acidic, or basic. So for A, we start with OH, so that means that we can have 1 times 10 to the negative 14 equal to, we're solving for H plus, times our 1.0 times 10 to the negative 5. So I'm not going to show it, but algebraically, you are going to divide over the 1 times 10 to the negative 5, so you would divide those out, and the concentration of the H plus is equal to 1.0 times 10 to the negative 9 molar. This is molar. So let's compare our hydroxide versus hydrogen. Well, times 10 to the negative 5 versus times 10 to the negative 9. Remember, when they're negative, the smaller one is bigger. So times 10 to the negative 5 is bigger, so that means that hydroxide is bigger than the hydrogen. So when hydroxide is bigger, it is a basic solution. Okay, well for B, we're starting out with 10 molar H plus. So we still use our 1.0 times 10 to the negative 14 equals 10.0 times the OH minus. So again, we're going to divide over the 10. So the OH concentration is equal to, when you divide out, 1.0 times 10 to the negative 15 molar. This is being on, sorry. Okay, let's compare. So the H plus is a 10 versus the OH, which is negative 10 to the negative 15. I'm pretty sure the H plus is bigger than the OH minus. So when H plus is bigger, it is acidic. And that's it. So on the quiz, just know that it's not all this kind of easy math. You have a lot of conceptual problems on the quizzes for this. So for homework, we have numbers 19, 36, 37, 42, and 45A and B to complete.